Okay, this is 7.4, evaluating and graphing sine and cosine, another really important lesson. So today's objective will be to use reference angles, calculators or tables, and special angles to find values of the sine and cosine functions and to sketch the graphs of these functions. Oh, this is big stuff. My calculator is in the other room, so when I get to a calculator problem, you guys are going to have to let me run and grab it real quick. Sorry about that. Anyway, let's get going. Okay, let alpha equal 30 degrees. Now I'm going to have a diagram of this on the next slide, but I want you to visualize in your mind right now an angle of 30 degrees in standard position. The terminal rays of alpha equals 30 degrees and 180 degrees minus alpha equals 150 degrees are, now picture those two angles now. One would be a quadrant 1 angle, 30 degrees, and one would be a quadrant 2 angle of 150 degrees. All right, and those two terminal rays would have symmetry in the y-axis. And again, I'm going to give you a diagram of that in just a moment. On the next slide. I didn't have room to put it on here. Anyway, here's where we're going. If the sine and cosine of alpha equals 30 degrees are known, then the sine and cosine of 150 degrees can be deduced. And that is the power of what we call reference angles right now. And I'll give you a definition of that in just a moment. So let's look at the picture of this. So here is my first quadrant angle right here. That's the terminal ray, all right? And so that's my 30-degree angle alpha right there that I have a picture of. So alpha equals 30 degrees is called the reference angle for, and this is a reference because if I know the coordinates of this point right here, then I know the coordinates of a whole bunch of other points on this circle. And it is the reference angle for, all right, well, what we talked about on the last slide, the 150 degree angle right there. And notice how I got that 150 degrees? Well, if this is 30 degrees on this side, then this would have to be 30 degrees right here. And 180 minus 30 degrees gives me 150 degrees. And then look at my quadrant 3 angle right there. Add 30 to 180 to get 210 degrees. And then look at your quadrant 4 angle over here. All right, and take 360 degrees minus 30 degrees. You get that angle right there. And that angle, that positive angle, would be 330 degrees. So if I know sine and cosine of 30 degrees, I know sine and cosine of 150 degrees, 210 degrees, and 330 degrees. And that is because of this. It's all based upon the coordinates of this point right there. And right now we're just going to call this point xy. Now, because of symmetry, that would make this point right here. Oh, let's set up our triangle too. Do you see this quadrant 1 right triangle right here? Well, the hypotenuse of my quadrant 1 right triangle will give me the radius of my circle. And then this adjacent leg right here, we call that adjacent because it is the initial ray of my angle alpha. The adjacent leg is x. And then this leg is called the opposite leg because it's opposite of angle alpha. And that's my y. All right, so look at everything I have right here. That point, x comma y, and then I have this radius of my quadrant 1 right triangle r. Now over here, what would the coordinates of this point have to be if this point has coordinates x comma y? Well, because of symmetry, the x coordinate over here would be the opposite of x, and the y coordinate would stay the same because I have the same height right there, y. All right. Now, how about here in quadrant 3? Okay, well, the x is still the opposite of x right there. And look at the y right here. This would be the opposite of y here. Okay, and then we go our final terminal point for the 330 degree angle right here. All right, and the x is still positive right there, so this would be the same coordinate. And the y, well, it'd be the opposite of this y, the opposite of y. And that is how we use reference angles. And I know this might look a little abstract to you, but wait till you see it in action. Hey, I'll tell you what, let me let my dog out of the office and go grab my calculator while I'm at it. Roxy, you do know that I'm recording a video right now, don't you? Go ahead. Okay, I'm back. The dog is out of the office and my calculator is in my hands. We're going to need our calculator a little bit later, so make sure you have it. All right, so this diagram, highlight it, put stars about it. This is pretty important stuff right here, and you're going to see how we use it when we put it in action in just a second. Okay, so let R equal, well, you know, the most easiest diagram and the most useful circle is called the unit circle right here. And that's a circle centered at the origin with a radius of 1. All right. Now, with that then, trig functions depend only on theta. All right. So the unit circle with a radius of 1 gives us the simplest diagram where cosine of theta equals blank and sine of theta equals blank. Well, let's go back to our algebraic definitions. Cosine of theta is x over r, all right? And sine of theta would be y over r. Now think about that. If the radius is 1, that means cosine of theta just equals x. So sine of theta is y over r. So there we go. Cosine of theta is just x right there. And that means any point on the unit circle, all right, has an x-coordinate of cosine of theta and a y-coordinate of sine of theta. That's powerful. By the way, sine of theta then equals y. Wow. All right. Very important slide right here. So cosine of alpha equals, now you guys don't know that yet, but alpha is a 30-degree angle right here, right? So I'm going to show you how to do this in just a little bit, but I'm going to give this to you early. See this horizontal distance right there? That would be this x-coordinate right there. And if alpha is 30 degrees, we know that that x-coordinate has to be a root 3 over 2. That equals x, and that x is root 3 over 2. Now I'm going to show you how to do that in just a little bit. Right now you're just going to have to trust me. Okay? Sine of alpha. Well, sine is this vertical distance right here of that angle alpha. So what is this y-coordinate right here? Well, I'm going to show you that too in just a moment. But sine of alpha is y. And y has to equal, guess what? This is exactly, if I'd drawn it perfectly, and this was drawn by hand, I did my best, but that has to be a 1/2. And I'm going to show you how to do that in just a little bit too. All right, so trust me for right now. Okay, so the acute angle alpha is the reference angle for 180 minus alpha, 180 plus alpha, and 360 minus alpha, just like we saw in this diagram right here with the 150 degrees, the 210 degrees, and the 330 degrees. All right, and you know what? We could keep just doing complete rotations in either direction over and over again. All right, so it's not only the reference angle for these 3 reference angles, but for infinitely many more. So here we go. What's happening right here? 180 minus alpha, 180 plus alpha, 360 minus alpha, and all of their coterminal angles. Wow. Okay, so express sine of 695 degrees in terms of a reference angle. So sine of 695 degrees. Well, let's visualize 695 degrees first. So here's my unit circle again. And check this out. This positive angle right here, well, I'm at 360 degrees. And then if I did one more revolution, I'd be at 720 degrees. So I'm a little short of 720 degrees right there. And that would be, if that's 695 right there, sine of, okay, now check this out. What's this negative angle right here? Well, again, 2 revolutions would be 720 degrees. So that angle right there is negative 25 degrees. So sine of 695 degrees equals sine of negative 25 degrees. All right, those are coterminal angles. All right, there are 2 angles, one positive and one negative, that have the same terminal ray right there. Okay, now they want us to express sine of 695 degrees in terms of a reference angle. Now, you need the definition of a reference angle here. So, a reference angle has to be a quadrant 1 angle, 0 to 90 degrees exclusive. Negative 25 degrees is a quadrant 4 angle. So, this is a graph of sine of x that I roughed out right here. It's not bad though. All right, and I'm going to use this graph of sine, which I'm going to show you how to do this later too, all right, to deal with something like sine of negative 25 degrees. Now, I hope you are noticing that sine has symmetry with the origin right there, all right. I could rotate this graph 180 degrees about the origin and be looking at exactly the same graph, all right. And that's the definition of an odd function. All right, so let's picture negative 25 degrees. Well, negative 25 degrees would be right in here somewhere. And picture that point down there on sine. Yeah, that's an odd function. Our reference angle must be acute. That means it must be in the open interval from 0 to 90 degrees. It must be a first quadrant angle, but not a quadrantal angle. All right, now there's this negative 25 right here, and what is the output? Well, let's think about this. The x-coordinate of that point is negative 25 degrees, and the y-coordinate of that point is sine of negative 25 degrees. Now, let's go to quadrant 1 and go to 25 degrees, right in here somewhere. All right, so what are the coordinates of this point right here? Well, the x is 25 degrees, and the y is sine of 25 degrees. Now, remember, sine measures my vertical distance. So look at this vertical distance, and then look at this vertical distance. Those are opposites of each other. And this is the case with any odd function. So sine is an odd function. So sine of negative 25 degrees equals the opposite of sine of 25 degrees. And now we have written sine of 695 degrees in terms of a reference angle 25 degrees right there. And that's what they're asking us to do right there. That's pretty cool stuff. Now cosine is an even function. So if they asked you, write cosine of negative 25 degrees in terms of a reference angle, you would say cosine of negative 25 degrees equals cosine of 25 degrees. But we'll see that a little later in the curriculum. Oh, this is fun stuff. Odd functions, very important, and this is your general rule for any odd function. F of negative x will always equal the opposite of f of x. Okay. Now here's where we need our calculator, all right? You know, if they give you sine of 122 degrees and so on, and they say approximately, they're expecting you just to punch these out on a calculator, all right? Now, before you do this, you need to make sure your calculator is in the correct mode. So hit the mode button on your calculator. It is just to the right of your second button. And right now, my calculator is in radian mode. So I'm going to click 2 arrows down and see the radians being highlighted, and then I'm going to arrow to the right. and I'm going to highlight degrees. Now my calculator is in degree mode, so I can punch out sine of 122 right on my calculator, and my calculator is going to know that that 122 degree angle is in degrees. So let me get that, close that. So I just go sine of 122. Now my calculator's not going to show me the degrees, it just shows me the 122. I have to make sure I'm in the correct mode, and that is approximately 0.8480 dot dot dot. And the 4 decimal places, I'm going to go 0.8480. There you go. Now cosine of 237 degrees. So let's hit cosine and 237. I'm already in degree mode still. And hit enter. And the 4 decimal places, I'm getting negative 0.4446. Excuse me, negative 0.5446. There you go. Now notice here, there's no degrees symbol. So that is not cosine of 5 degrees. That's cosine of 5 radians. So go back to your mode button and highlight radian, arrow 2 down and hit enter. All right, now you're in radians, and find your cosine button and just go cosine of 5. Now notice it just says cosine of 5. You need to know what mode your calculator is in before you hit enter. We're in radians, so just hit enter. And that's going to be, to 4 decimal places, 0.2837. All right, same thing for sine of negative 2. Sine of negative 2 radians. And that's going to give us negative 0.9093. And there you go. There will be probably one problem on your test where you get to use your calculator. Make sure when you do that, your calculator is in the correct mode. Okay, now this, I'm probably giving you guys a printout of this, or at least when we're remote, a link to a printout of this. But this gives us the radian measure of each of these terminal rays are right here on the in the unit circle. So what this pi over 6 means right here is that this angle right here is pi over 6. All right, so let's complete all the radian measure of these key angles. So my first angle right here, that would be 0 radians. 0 radians is the positive x-axis right here. And then we have pi over 6 right here. All right, and then this angle in the middle of quadrant 1, that's pi over 4. And then this angle would be pi over 3. And then you get to the equivalent of 90 degrees, and in radians, that is pi over 2. Now notice how I did the terminal rays here, the colors, because this terminal ray right here is going to be, well, there's pi over 3. This one would be 2 pi over 3s. And then I have 3 pi over 4s. Check that out. There's 1 pi over 4. There's 2 pi over 4s, which is pi over 2, and that's 3 pi over 4. And then this angle right here will be a multiple of pi over 6. How many? Well, 1 pi over 6, 2 pi over 6s, 3 pi over 6s, 4 pi over 6s, and that's going to be 5 pi over 6s. And then you have pi, and then you have 7 pi over 6, and I even gave you that in degrees, 210 degrees. And then what's this one? Well, it's going to be a multiple of pi over 4. Let me see, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. There you go, 5 pi over 4. And then your multiple of pi over 3, and that would be 4 pi over 3s. 1, 2, 3, and 4. And then your 3 pi over 2. You see the 1 pi over 2, the 2 pi over 2, or pi, and the 3 pi over 2. And then this is going to be another multiple of pi over 3. How many of them? Well, it might be easier to count this way and go, okay, that would be a negative pi over 3, which would be what? 6 pi over 3 minus pi over 3? That's a 5 pi over 3 right there. All right, and then you have 7 pi over 4. And then you have a multiple of pi over 6. That's a whole bunch of pi over 6s. I don't want to count them all. I'm going to go this way. This would be negative pi over 6. So I'm thinking 6 pi over 6 minus pi over 6. That'd be a 5 pi over 6. Or excuse me, what did I do? 12 pi over 6 minus pi over 6. That's 11 pi over 6. Don't get sloppy, Gibbons. And there is your unit circle with those radian measures for all of those terminal rays. All right, this is good stuff right here. And you're going to have this memorized. You're going to see one of these angles, and you're going to know what the radian is immediately, I promise you. All right, now this diagram right here. This diagram could be the most important thing I ever learned in trigonometry. This is a diagram of the first quadrant of the unit circle. This pattern gives us every output of every key angle on the circle. And again, could be the most important thing I learned in trigonometry. Now, it's very simple. On the unit circle, remember, the outputs or the coordinates of each of these points right here on the unit circle, well, the x is the equivalent of cosine of theta and the y is the equivalent of sine of theta, like I wrote right up here. Now, let's figure out the x coordinate of each of these points, and it's a simple pattern. All right, and the x coordinate of this point right here is going to be, and look at how I write this. It's 0, you know that, right? But I'm going to write it. Cosine of theta is x over r, all right? And r is 1, so cosine of theta is just x, and that's going to be a 0. And I'm going to write that 0 as a root 0 over 2. And that is because, again, why does cosine of this angle right here equal 0? Well, cosine measures horizontal distance, or my x, and x is 0 at that point. So this is called a degenerate right triangle right here. It's a right triangle without a base. The base is 0. Now, let's go to this point. And I did not draw this perfectly to scale, but we'll label everything right here. And here's the pattern. Guess what the x-coordinate of this point is? It's 1/2, which I'm going to write as root 1 over 2. And that is because if I had drawn this perfectly, look at my right triangle right here, based upon that terminal ray right there. All right, this horizontal distance right here should be exactly 1/2. Okay, now I hope you see the pattern. Make a conjecture. How do you think I'm going to write the x-coordinate of this point? Root 0 over 2, root 1 over 2. That's right, root 2 over 2. And let's draw our quadrant 1 right triangle based upon this terminal ray right there. All right, and guess what? This horizontal distance right here is exactly root 2 over 2. Now let's continue the pattern. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2. And look at our quadrant 1 right triangle based upon that terminal ray. And this horizontal distance right here, root 3 over 2. That's the adjacent leg of that angle right there. All right, now one more. And you guys tell me. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2. Guess what? Root 4 over 2, which is 1. And that's because we have another degenerate right triangle. This is a triangle with a base but no height. And this base has a length of, on the unit circle, that would be 1 unit. And the square root of 4 over 2 equals 1. But we write these this way so we can see the pattern. Now guess what? Corresponding y coordinates. The pattern is the same. We just go in a different order. We reverse it. All right? This point right here, the y coordinate, well, there's no height right there. That y is root 0 over 2. And we're doing that because sine of theta is y over r. And on the unit circle, r is 1, so sine of theta is y. What's the y coordinate of this point right here? It's a 0. But we're going to write that as root 0 over 2, so we see the pattern. And let's make sure you see that again. See my degenerate right triangle right there? The height of that degenerate triangle is 0. Okay, now here. Guess what? Root 0 over 2. This one's going to be root 1 over 2. And let's draw our quadrant 1 right triangle with this terminal ray right there. And you see this height right here? Had I drawn this perfectly, that height would be exactly 1/2. Okay? Now this one, root 2 over 2. That's right. And look at your quadrant 1 right triangle right there. This height is exactly root 2 over 2. All right? And then we go here, and yeah, you're right, root 3 over 2. And that's because this right triangle, this height, had I drawn it perfectly, is root 3 over 2. And then finally, root 4 over 2. And that's because this degenerate right triangle right there, that right triangle with no base, it does have a height, and that height is 1. And we're writing that one as root 4 over 2, so we see the pattern. So these are the key angles on the unit circle that we use for reference angles, including our quadrantal angles of 0 degrees or 0 radians, and then this one 90 degrees or pi over 2 radians. This is, again, could be the most important thing I learned in trigonometry. It allowed me to find the outputs of sine and cosine and every other trig function on every key angle on the unit circle. Okay, so let's look at this now. Sine of pi over 3. Now, can you visualize where pi over 3 is right here, right now? And we're talking radians. 0 radians, pi over 6, pi over 4, pi over 3. There it is right there. So sine of pi over 3 is, well, you see that root 3 over 2? Cosine of pi over 3 is, do you see the root 1 over 2? Which I'm going to write here as 1/2. There you go. That's how we use this. Really powerful. Okay. Let's graph sine and cosine without our fancy graphing calculator. All right? Now, it's really simple to do if you understand what we've been talking about on the last 2 slides here. All right? So, we're going to use positive quadrantal angles and periodicity. So I'm going to draw a picture of the unit circle right here. So this is a circle with a radius of 1, the unit circle right here. All right? Now, positive quadrantal angles. Which one do we want to graph first, sine or cosine? Let's graph sine. So think about 0 and see the pi right there. I'm going to use radians. So 0 radians right here. What's the height at that point? It is 0. So when theta equals 0, y equals 0. So that's the point 0, 0. That's where sine begins. Now let's go to pi over 2. And what's the height right here? Because remember, y equals sine of x. All right? That height is 1. So at pi over 2, let's put a point up here at 1. And then let's go to pi. There it is right there. Okay? And what's the height at this point right here? Well, that y is a 0. So we're coming back to 0. And then let's go to 3 pi over 2. Right there. And what is this vertical distance right there? That would be -1. So at 3 pi over 2, we'll have a point down here at -1. And then at 2 pi, we are back to 0, no height. So there it is, 0. And that is the first period of y equals sine of x. Now, because of periodicity, that pattern will travel forever in both directions, forever and ever and ever. So most people, when they are asked to graph sine and cosine, they graph them in the window from negative pi over 2 to pi over 2. So let's just repeat this pattern to negative pi over 2. And there it is. There is the perfect graph of y equals sine of x. Now, let's put cosine on the same graph. So cosine, I'm using my positive quadrantal angles, but now I'm thinking horizontal distance. So do you see the 0 radians again? Right there? That distance is 1 unit. So at theta equals 0, I'm going to have an output of 1. Now let's go to pi over 2. What's the horizontal distance right here? That's 0. So let's put a point right there. And then let's go to pi. There's my pi right there. And what's this horizontal distance? -1. All right? And then let's go to 3 pi over 2. Right there. What's this horizontal distance right here? Well, the x-coordinate of that point right there is 0. 0. And then we get back to 2 pi, which is equivalent to 0 radians right there. And again, my horizontal distance right there is 1 unit. Now, this scatter plot of blue points right there, let's do the smooth curve. And there you have it right there. And periodicity again, let's go ahead and repeat that pattern from 0 to negative 2 pi right there. And those patterns go on forever and ever in both directions. Those are great graphs of y equals sine of x and y equals cosine of x. And then again, if you use your calculator to graph y equals sine of x or y equals cosine of x and you hit trig window, it's going to give you exactly those two graphs right there. Okay, now you guys have fun. Do these problems carefully. Make sure you understand this stuff. This is page 279. 1, 5, 11, 13, 15, 17, and 22. Have fun. Drop me an email if you have any questions.